Okay, I've divided the hypothesis test for means examples into two parts. So here we're looking at part two, and a couple of things I want to emphasize here: the connection between a two-tailed test and a confidence interval, because they can mean the same thing. If your test is one-tailed, whether it's right-tailed or left-tailed, and then you have an accompanying confidence interval, they might not mean exactly the same thing. Okay, but if you have a two-tailed test, that's 5% significance, which is what we're going to do here. We're going to use alpha equals 0.05. This will give us the same conclusion, or it should, as a 95% confidence interval, because it's two-tailed. If it's one-tailed, it will not. Right? We want to be careful with that. Remember, with two tails, this 5% gets divided by 2. So just like a 95% confidence interval, 2.5% in each tail. Okay. If alpha is 10% two-tailed, that's like a 90% confidence interval, and so on. 1% would be analogous to 99%. So the first question is should be review. I'll write my answer up here, but all I want to do here is just interpret the standard deviation and the standard error provided in the computer output. So let's make sure we understand the narrative here. This children's game, I don't know if anybody's ever played this. Probably sure you can find it on a shelf at Target somewhere or something similar to it. But you have these cubes that you have to put in place, almost like a kid's version of a Jenga probably. And they have to have a pretty tight fit. They're going to fit pretty precisely, and you're trying to not have the whole thing collapse as you tap on a cube, an ice cube, with the hammer. So that's our context, not terribly complicated, but they want to check to make sure that the cubes are being produced close to the true population mean, or what they expect the population mean to be, mu, 29.5. So if we had a claim here, the claim would be, and we'll get to that in the hypothesis test, mu equals 29.5. And again, this would be a two-tailed situation, because we don't care if the cubes are too big or too small. If they're too big, they don't fit, and if they're too small, they don't fit, and then it doesn't work. So the first part should just be review. Part A, interpret the standard deviation. So what does this standard deviation of 0.09 mean? It means, on average, in this sample of 50, it's a sample standard deviation, right? When I take any individual cube from this sample, it should differ from 29.4846, the sample mean of the 50 cubes, by about 0.09 millimeters. Okay, that's what that means. Now, the standard error, right? Where does that come from? They took the 0.0900274 and they divided that by the square root of 50. Okay, that's where this 0.0127318 comes from. Now, that's just a computational interpretation. What does it mean in context? It means we don't know that this is true. We believe that it is. But what we believe is that this 29.486 or any other x bar, right? If we go and get if we believe 29.5 lives in the middle here, or whatever mu is, that we got this one x bar, and the standard deviation of all these x bars, okay, sigma x bar, okay, is this 0.0127. It's smaller, right? When we take a sample of 50 and average them, we expect them to be a little bit closer to the mean than if we just took one at a time. So that's why the sample standard deviation is larger than the standard error. But that's the interpretation of them. That should just be review. So now for part B, I'm going to go to my template. So mu is going to be the true mean diameter, I think, not width. No, it is width. It was right the first time. The true mean width of cubes produced in this hour. Right? Because if we look at the question here, produced during this hour, they took a random sample of 50 cubes every hour, okay, and measured their width, or measured their mean width, okay. So that's where our sample is coming from, so we want to specify. And I think we referenced this already. The null hypothesis is going to believe that they're making these cubes the way that they ought to, that the mean is 29.5. The game is not going to function the way it ought to if it happens to be different from 29.5. Doesn't matter if it's bigger or smaller, okay? Let's start with the SRS, because we have that right in the narrative. We can put it in quotes. Random sample of 50 cubes. Right, we just put that in quotes. They told us they took a random sample of 50 cubes. And we put that in quotes. Okay, we can assume that 50 is less than 10% of all cubes produced in that hour. All right, we'll just add in that hour to that. And again, we have to assume this. Right? If you want to put the word assume there, you can. And then finally, for normality, this makes our life a little bit easier. 50 is greater than 30, so we can cite the central limit theorem. We're good to go. I don't need to make a box plot, in other words, and I really can't because I don't have the data. Okay, so this is a t-test. Remember that t equals statistic x bar minus parameter mu divided by the standard deviation of the statistic. So they give us all of this. Right? We can express this however we would like, but they give us everything we need here in this printout. There's our x bar. Okay, we know mu is 29.5, and we can either use the 0.09 divided by root 50, or we can use the 0.0127318. Doesn't really matter. Either way, I just put my formula there. I'm going to, and we don't have to plug into it, just like to write the formula out. So I'm just going to calculate my test statistic. So I'm going to go to stat. I go over to tests, and this is just a t-test, number 2. Okay, so I do not have the data like I had in the last one. This time I have stats. The null hypothesis for the mean is 29.5. The alternate hypothesis, or the I'm sorry, the sample mean is 29.4846. Okay, that was their sample mean. And be careful you put the right number here for your sample standard deviation. It's the 0.09. 0.09000274 if we want to be really precise. And don't use the calculator is going to take that and divide it by the square root of 50 for the formula. And it's a two-tailed test. Okay, so this is always sample standard deviation. Do not use the standard error there. Calculator will get the standard error itself. Okay, it doesn't provide it for us in the printout. Just gives us our mean and our standard deviation. But it gives us our p-value, 0.32 or 0.232, and a t-statistic of negative 1.2. Okay, so I'm just going to write down that t is negative 1.2, right? So for 49 degrees of freedom, we get a p-value of 0.232. And that's all we need to make our interpretation, right? We are going to, in this situation, say that we fail to reject H0. And remember, I don't know if they cited it, but I'm going to use alpha as 0.05 so I can show you how this connects with a confidence interval. We would fail to reject H0. Okay, be careful with the language you use here. I'll often have people say that we proved H0, or we have convincing evidence that H0 is true. That's not what happened here. Right? We do not have convincing evidence. Right? We were looking for evidence that H0 was not true, and we don't have that. So if we fail to reject H0, this means that you should immediately start with we do not have convincing evidence. Okay. We don't have evidence to contradict that. Right? So it appears the machine is working. That's their question ultimately. They want to know, are we making the cubes the way that we would want to be making them? So as we move into the confidence interval part of this, that's going to be the follow-up question to this. So this whole entire part B is on my template. It's done. Okay. If you take that, what I have on my template there, and put that in for part B, that's start to finish what we would want there. Now, when we take this to the confidence interval, what we should have is we should end up with a confidence interval that contains 29.5. When I put my confidence interval portion in here, I should find that my confidence interval contains 29.5 since I was unable to reject the null hypothesis that it equals 29.5. That's what we should already be starting to think that. All right, so we have here the confidence level of 95%, and they actually even give us the they give us the confidence interval. They tell us it's 29.4846 plus or minus. They already did the margin of error for us. And then here's our lower limit and our upper limit. Okay, so it just says interpret the confidence interval, right? So we are 95% confident that mu, and we already said what mu was, is contained in this interval. It's the true mean width of cubes produced. So mu equals 29.5 is plausible. Doesn't mean I proved it. We just don't have evidence to disbelieve it. If we had an interval that did not contain it, then we would be 95% confident that that 29.5 is not true. Okay. And then part B, interpret confidence. What does that mean? Okay, this is probably the hardest part of chapter 8. If we made many of these intervals, if we made 100 of these intervals, about 95 of them would contain mu. AP exam tip, watch for something like this on like the multiple choice. I'm hoping to have a good amount of time, and anybody that wants to start reviewing for the exam and doing some practice mock-up exams where I kind of walk you through, there's a lot of strategies I give out. The first one being when you open that multiple choice, I don't recommend that you just sit down and do number 1 and then do number 2. I recommend that you look over it. What you're going to see is like in the first 10 or 12 problems, you're not going to see a lot of numbers. What I tell students to do is skim through them, and if you don't see any numbers in the question, do those first, because they're completely conceptual. And if you've committed the time and put the effort into understanding the concepts here, you'll be fine. Answer the conceptual ones first, because then you won't get bogged down with any computation. You're not going to have to go find normal CDF or binomial PDF or binomials. You won't have to do any of that. You just answer conceptual questions. And you can really strategize and save your time and maximize it for things that might be more time consuming. Same thing with the open-endeds. I tell students to read through, don't read them word for word, but just skim read and then say, oh, here's one on linear regression. That's really hard for me. I'm going to save that to the end. Oh, here's one where I'm going to do normal CDF. I'm going to do that first because that's really easy. Find the ones that are easy in your wheelhouse. Do them first and then leave the tougher ones towards the end. So it's a better way to maximize your time. But we're in a position now where we'll be able to start practicing like that. Now, one of the most important things we need to be able to do, whether it's in an AP exam or just applying statistics in general, especially if many of you are going to be pursuing fields in science, business, anywhere that you're trying to interpret research, what kind of statistical tests do I use? And what we're going to see in chapter 10 is that sometimes we have two different populations that are independent of each other. Like suppose I wanted to compare average SATs at Eastern High School to average SATs at Cherry Hill West High School. Those are two different populations. What I find in this example is I actually don't have two different populations. These two lists here are not independent. So all we're going to have in this situation is a one sample t-test where we're comparing their differences. This is a matched pairs situation. So what I need to do first and foremost is find a third list, right? What these two girls did for their AP Statistics end of the year project, they went at 15 different times during a week. So they went to the same store, okay, bought the same item, and they went at the same times, okay? So this 342 and this 337 are not independent of each other, all right? They have a lot of things in common. Now, they applied randomization to their experiment because they flipped a coin to decide which lane each one would go. So in other words, Libby didn't always go to regular and Catherine always express. They flipped a coin because that could be a lurking variable of how it affects their times. And now they have a hypothesis. Carry out a test to see if there's convincing evidence that the express lane is faster. Okay, so if the express lane is faster and my differences are going to be, let's just do it this way, regular minus express. This is going to be important. If I subtract them into different, this is a one-tailed test because they're trying to see if it's faster, not just different from. So if I do regular minus express and express is faster, then I'd expect the regular to take longer than the express. These are the amount of time they spent. Okay, so my regular minus express, this is going to be really important in formulating our alternate hypothesis, I'm going to expect this to be greater than 0. If I did express minus regular, I'd need that alternate to be less than 0. We want to pay attention to that right away. So the first thing I'm going to do is go to my calculator. I'm going to go to Stat and Edit. So this is a little bit more of a time-consuming question here because we're going to have some data entry involved. Clear my lists, and I'm going to go ahead and put those two lists in my calculator. Now, I could, I suppose if you want to, you could just do 342 minus 337. You could subtract them here. And do it that way. That might actually be quicker. But that's what we need ultimately is a list of differences. If I put this list in L1 and this one in L2, then I can just hit L3 equals L1 minus L2 and it'll populate the list. So whether this is quicker or not to use my calculator, I'm do it anyway just so I can show you for the exercise. But make sure L3 is highlighted and press enter. So it says L3 equals, and then you're going to hit second, L1 minus second, L2. On the Inspire, you can do the same thing. You just go up there and press the equal sign, and you type that function, and but you have to name your list. Make sure you name the lists like reg and exp, and then you should be fine. So I press enter, and that's the list that I'm going to t-test. Okay, so I want to get my template out now. I'm going to do this whole hypothesis test start to finish on my template. Actually, it might be good. Let's see if we can take the training wheels off here and see if we can recall our template ourselves. Very first thing we ought to do is identify our parameter. And notice I don't just use mu here. Now I use mu sub d. Now, if you didn't use mu sub d, I don't think it warrants taking off points, but make sure that you articulate this parameter correctly. All right. This is the true mean what? It's the true mean difference in time at checkout. And what did we do? We did regular minus express. I want to specify that. It's a difference. All right, so every time we go and we subtract how long it would take and express from regular, we're taking the average of that. Okay. Our null hypothesis, or null hypothesis is going to be that mu sub d equals 0. It doesn't matter what register you go to. It's going to take the same amount of time. They believe that express is faster, so when we do regular minus express, we already stated this, mu sub d should be less than 0. Okay. Did they take an SRS? Let's go back to the narrative and see. All right. To collect their data, they randomly selected 15 times. So we're good. Put that in parentheses. Right? They randomly selected 15 times. All right, so we got our randomization piece. Okay, there's certainly 15 times is less than 1/10 of all possible times. Seems like there's probably almost infinitely many times they could pick from. And then finally for normality, okay, they only took 15 times, so we need a box plot. But what do we want a box plot of? All right, here's where you would lose points. If you did two box plots, one of L1, one of L2, that's going to be wrong. Our parameter of interest is the differences. So I'm going to go to my stat plot, I'm going to turn it on, and I want certainly a box plot modified. If there are outliers, we'll see them. But I want the box plot to be one of just L3, just the differences. That's important, okay? So everything looks good with the world here. To get my graph, remember the shortcut is zoom 9, right? Looks like I have some stuff in my calculator I don't want. So a little bit of a tail to the right, but I don't think anything alarming. We don't have any outliers, and we don't have to bother with the 1.5 IQR rule. Again, we can hit trace here and get ourselves our 5-number summary so we can make a nice accurate graph for anybody that's looking at our work. And I cheated a little bit. I used my stipping tool, but box plot is roughly symmetric with no outliers. Okay, so some of you are saying it's not roughly symmetric, it's slightly skewed. It's fine. You think it's slightly skewed, you can say it's slightly skewed to the right. Either way, remember, what's the point of this exercise? is the t-distribution, is the assumption of normality satisfied? And the answer to that is yes. That's all I'm trying to do, is make sure that my sample size isn't small with lots of outliers. If that's the case, then the t-distribution puts us on shaky ground, and our inference could be invalid. So all I'm trying to do here is make sure that it's a viable assumption to go ahead and use a t-distribution. So with a sample size of 15, even though that's a little bit skewed to the right, it's going to be okay. Right? And notice I didn't say it was exactly symmetric or very symmetric. It's roughly symmetric. Okay. So we're just checking those conditions, and then we're moving on. All right. So this is a t-test. All right. What does t equal? X bar, the sample, minus the parameter mu, divided by the sample standard deviation over root n. Same thing. You're going to do these so many times that you probably won't have to look at your formula sheet, okay, especially if you study and drill for the exam. So we'll go ahead and run our t-test now. We had to do a little bit of heavy lifting there in the beginning by putting the numbers in, but once my numbers are in, we're ready to go. And this time we do indeed have data. So I'm going to select the data option there, and my data is in L3. However, we're not testing against 29.5, we're testing against 0. And this is one-tailed. We wanted to see if the express lane is faster. So our alternate was that it's going to be greater than 0. So I have to pick that in the same direction. If you get a p-value of like 0.99 something, right? If you ever get a really high p-value, that's usually a tip-off that you did a one-tailed test and did it in the wrong direction. All right, so I get a small p-value, 0.0347, and a t-value of 1.97. And let's look at that p-value, 0.035. Okay, so they never told me what alpha is, so I'm just going to pick one. Let's go with alpha 0.05. We'll reject H0. Okay, what does that mean? It means the girls have significant evidence that the express lane is faster. Right? The null hypothesis was that the average difference was 0. Our alternate was that it was less than 0. I think I wrote that wrong. It should be greater than 0, right? When we subtract regular, it should be greater than 0. Glad I caught that before the video is over. Mu sub d greater than 0. We did it right on our calculator, but we would expect that express, and we wrote it over here also, that difference, regular minus express, to be greater than 0. Okay, so we reject H0, and that means now we look at what our alternative was, and that's what we're going to choose to believe in.